Hello, I'm going to talk about our paper, Improve Neural Protoform Reconstruction via Reflex Prediction. To get a bit of context, think about a time when you look at two things and realize they look similar. I wonder if they are related. Sometimes people look at species, and that has led to some great discoveries. Sometimes people look at languages. They're just similar meaning words in two languages that also sound similar, and we start wondering if they are related. It might just be a coincidence, but perhaps after looking at many pairs of words, we start seeing some pattern. After some time, we do enough comparisons, eventually being able to piece together these patterns to reconstruct what happened in the past. This is how we are able to develop the fields of evolutionary biology, population genetics, and historical linguistics. They open up a window into the rich history of planet Earth and human development. Historical linguistics, in particular, shed light upon how languages and culture evolve together over time. Before jumping into how we reconstruct the history of languages, I think it would be helpful to look at a few definitions that we will use throughout the presentation. We refer to a historical language as a proto-language, and its modern descendants as its daughter languages. The protoform of a word is what we believe it looked like in the proto-language. This is usually a reconstruction, but it can also be the actual ancestral form if we know it. For a given protoform, we call its descendants its reflexes, and the set of reflexes in the same protoform form a cognate set. Looking back at the goat example I flashed earlier, here we have the protoform capra, meaning goat in the proto-language Latin, and its reflexes in four daughter languages. We have capra in Italian, cabra in Spanish, cabra in Portuguese, and chèvre in French. All these four reflexes together form a cognate set. After gathering many cognate sets, historical linguists use this method called the comparative method to reconstruct protoforms. At its core, there's this assumption that historical sound changes are largely regular and that most reflexes can be derived deterministically from the protoform via a series of sound changes. So for the reconstructions we come up with, we would want these sound changes to be as regular as possible. At the same time, we want plausible protoforms that don't deviate too much from the reflexes. Comparative reconstruction can be an extremely laborious process, especially when there are lots of cognate sets to look at. Unsurprisingly, there has been many attempts to automate this task computationally, including by using probabilistic models, sequence comparisons and alignment, and conditional random fields. Maloney et al. 2021 views protoform reconstruction as a sequence-to-sequence task, which we know how to model with neural networks. What they do is that they concatenate all the reflexes into one long sequence like this and have an encoder-decoder RNN model predict the reconstruction. And that started a whole line of research looking at how to build neural reconstruction models. Kim et al., for example, replaces Maloney et al.'s RNN with transformers, and Cui et al. Adds an VAE component to Kim et al.'s transformer to obtain improved encoding of the daughter sequences. These can be largely described as sequence-to-sequence modeling. The more recent cognate transformer architecture does something a bit different. They stack sequences on top of each other and feed it through a protein language model and uses the encoding to predict protoform tokens that has been masked out. An observation here is that when performing reconstruction, these models largely follow the setup of just taking in reflexes and producing a reconstruction. Well, in some sense, historical linguists do this. They look at reflexes and propose a possible reconstruction. But are they done here? Probably not. Earlier, we said that we want the reflexes to be derivable from the reconstruction. So historical linguists need to make sure that that is the case. They ask themselves, does my reconstruction make sense? Can I recover the reflexes from my reconstruction? Seeing this difference in workflow, we ask the question of whether it really makes sense for the computational model to just stop at reconstruction. And our answer is no, we shouldn't stop here, and a more complete implementation of historical linguists' workflow makes a difference in computational reconstruction. What we propose is that we add an additional model to check whether the reflexes can be derived from the reconstruction model's predictions. And to implement that, we need a reflex prediction model. This brings us to another line of research on computational reflex prediction. For reflex prediction, some existing methods include rule-based systems, automatic alignment and sound correspondence identification, and finally neural networks with RNN and transformer models. This is the method that we'll be using. Similar to reconstruction, neural reflex prediction can be represented as a sequence-to-sequence task. The major difference here is that the input is now in a single language, but we want to predict multiple different daughter languages. So we prepend the daughter language token to specify which language we want to predict the reflex for. With all these pieces, we're now ready to revisit the neural protoform reconstruction workflow, which up to this point mostly involved just predicting the protoform. In our improved system, however, we follow a three-step workflow. First, we come up with multiple potential protoforms. We can do this by running beam search on a sequence-to-sequence reconstruction model. Then, we want to verify these proposed reconstructions by estimating how well we can recover the reflexes. We use a neural reflex prediction model for this. Finally, we used reflex prediction results to identify the most promising reconstruction, namely through re-ranking. So here it is in action. We start with reflexes in a coordinate set. We then use beam search to obtain a few possible reconstructions. Here we show a beam size k equals 5. Notice that the highest scoring prediction is incorrect, and the target protoform we're looking for is at the third place. Now, we take these candidates and use reflex prediction model to see what reflexes we get back from each candidate. Autopilot. We check the predictions. The reflex prediction accuracy is going to be our re-ranker score. And thus we also refer to the reflex prediction model as the re-ranker. Finally, we calculate an adjusted score for each candidate by taking a scale sum of the model score, which is just the log probability from beam search, and the re-ranker score. We sort the candidates by their adjusted score, and this will be our re-ranking result. So here we successfully identify the correct protoform reconstruction. So this is basically our entire reconstruction system. To test how well this works, we run experiments on 5 datasets. We use 2 Romance datasets for Latin reconstruction. It's the same coordinate sets but represented 2 different ways. A phonetic version in which words are represented as IPAs, and an orthographic version. We use 3 Sinitic datasets for Middle Chinese reconstruction, including WikiHan, an augmented version of WikiHan, and the whole dataset. We use Maloney et al. And Kim et al. As our reconstruction baselines, and we implement beam search for Maloney et al.'s GRU model so that we can get those candidate reconstructions. For neural reflex prediction models, we're not aware of one designed for any of the languages we're interested in, so we adapt 4 different models to do this. 2 of them are transformer models, 2 other ones are GRUs. One of them is a baseline model modified from Maloney et al. With a number of experimental changes to account for the fact that we're mapping from one language to multiple daughter languages. More detail on the slide or in the paper. We use the same evaluation metrics as previous work on reconstruction. We have standard ones like accuracy and token edit distance. Normalizing the token edit distance gives us token error rate. Feature error rate is like token error rate, except the edits are phonological features rather than tokens. And we measure this with panphone. Lastly, we use B-cubed F-score to measure the structural similarity between the predictions and the target. To test for statistical significance, we use both Wilcoxon and Bootstrap tests with an alpha of 0.01 and a confidence interval of 99% respectively. We consider a result to be significant if indicated by both tests. We first tested just the reflex prediction models to decide which ones to use in our re-ranked reconstruction system. Overall, transformer models seem to be doing better than GRUs, though our GRU baseline is often not too far behind. We proceed by selecting the best models from each architecture as the re-ranker model, which are baseline GRU and Aurora et al.'s transformer. Using these two models as re-rankers, we compare the performance of different reconstruction systems. On all datasets, our re-rank reconstruction system performed the best. Our accuracy improvements over the baselines are in the range of 1 to 3% points. It is interesting to see that the re-ranked reconstruction performance on the augmented version of Wikihan is more than 1% higher than the unaugmented version. The improvements are quite consistent across metrics, so I won't go into detail. And regardless of the re-rankers architecture, they perform significantly better across all metrics on all datasets except for Hull. To make sure that the improvement comes from re-ranking rather than from beam search, we perform an ablation where we take away the re-ranker and just return the highest scoring candidates from beam search with k equals 0. What we find is that beam search with re-ranking performs significantly better than beam search without re-ranking. This is likely an indication that the reflex prediction model is quite effective at identifying the correct protoform compared to the reconstruction model's own learned parameters. To dive deeper into what the re-ranker is doing, we study 4 disjoint categories based on how the re-ranker changes the ranking of the target protoform. Not in is when the target protoform does not appear in the beam search result. In this case, there isn't anything the re-ranker can do to produce a correct prediction. Unchanged is when the rank of the target protoform is the same before and after re-ranking. Improved is when the re-ranker pushes the target protoform up the ranking, and worsen is the opposite. Just by counting the number of test examples in each of these categories, we see that it is not very frequent that the re-ranker changes the rank of the correct protoform. Depending on the dataset, it's only about 5 to 25% of the time. But when it does, it's quite often that it improves the target protoform's ranking, making it more likely that we predict the correct protoform after re-ranking. One pattern we notice in our system's reconstruction errors is that incorrect protoform predictions tend to be phonetically closer to the reflexes. In this table, we compute the percentage of test examples where the similarity between the reflexes and the predicted protoform is higher than the similarity between the reflexes and the target protoform. We see that the worsened category has the highest percentage. It is possible that in some cases, the reflex prediction model finds it easier to recover the reflexes if the proposed protoform looks more similar to the reflexes, even if it's incorrect. Here, I've selected a few error entries where the prediction is more similar to the reflexes. With mu, we see that the gold protoform has a ya sound that gets deleted when editing towards the reflexes. The reconstruction system decided to not include that ya. There are also situations where the reconstruction system predicts affricates more similar to the ones in the reflexes. Likewise, in romance, we see that the reconstruction system sometimes prefers not predicting a phoneme that is not present in most reflexes. Despite these errors, the re-ranker is still quite informative in most situations, leading to overall better reconstructions. In conclusion, we realize that many efforts to automate proto-language reconstruction with neural networks have treated reconstruction as a fairly generic sequence-to-sequence task. Ironically, they make little attempt to replicate the centuries-old comparative method used by historical linguists. Our proposed re-rank reconstruction provides a more complete implementation of the comparative method, in particular by implementing the constraint that reflexes should be inferable from the reconstructions. By upscoring reconstruction candidates from which reflexes can be correctly derived, we achieve reconstruction performance that surpasses existing methods. If there is one takeaway from our paper, I would say that it's helpful to keep in mind linguists' methods when developing computational linguistic systems, as incorporating linguists' workflow can sometimes lead to actual improvements. To learn more about the detail of our re-ranked reconstruction system and experiments, you can check out our paper and code. Thank you so much for joining me today.